Hello there. Let's do a quick review for our Math for Engineers. While we are covering some part of it, I'm sure you're going to cover some part of it in your contact sessions. Our treatment of mathematics, pretty informal. We are not looking at learning it right formally. So if you're looking at serious treatment for mathematics, this is not the session. However, we'll do enough mathematics that our test engineers are able to fly. What does mathematics do for us? Brings in rigor, precision, and efficiency. These are the three things that we would want to look at. So let's see how we could make our craftsman, the test engineer, better at his craft. So we start off with permutations. You saw permutations and combinations. Permutation was about the lock and combination was about the fruit salad. We have repetition and without repetition. That is how we could choose R things out of N things. And these are the formulae. On this page, you've got the formulae for permutation, and then you've got a formulae for combination. Thus, number of inputs from a set of inputs that could be given for a few variables, you could start making permutations and combinations. These permutations and combinations will serve a purpose when we are looking at software testing. Next, we look at the propositional logic. A propositional logic or a statement will be either only true or false. Thus, we start communicating in a manner that we are precise. And by now, I hope you have found out this if-then piece. If not, now is the time to find out, because it has unique properties. And then you have got the regular ones which are AND, or NOT, and the XOR. For P and Q, those are the relationships that you see and the outcomes based on propositional logic. Further, we looked at set theory. Collection of things with a common property. With, say, months in a year with 31 days. Is this correct? 31 days? April, June, September and November? I think it should not be 31 days. It should be 30 days. We also use decision rules over here, stated in this manner. How a set theory is useful? For all the inputs and their sets, as we looked at, and especially I'm going to now double it up with the Venn diagrams that we see. If this represents a set of population, then I'm looking at male-female distinction, and I'm looking at children, adult, and senior citizen, children, adult, and senior citizen distinction. Now I can represent it with pictures. If each of these triangles and the size of the triangles represent the magnitude, then I've got a pretty accurate representation. Venn diagrams, which allow me to show something is X and Y, so I've got A and B, so there's an intersection part which talks of, yes, what are we talking about over here? So if you have got males and females, here you have got the number of children maybe. That would be the intersecting point. All children were either male or female. And then there are set operations which allow us to go ahead and do certain operations which are useful to us, which is union, intersection. Union would help us put together things. Intersection would be only the common between the two. Complement, which is not something. So and so forth. Other set operations are to do with the unordered and the ordered pair. Ordered pair, unordered pair, ordered pair of inputs that need to be given to a particular program. Set relations. A set is a subset of B. In that it would probably also be equal sets when each set is a subset of the other. I urge you to look at more definitions, and this set theory, equivalence class partitioning, domain testing, that is where these sets would be very, very useful. Next, we move to graph. Linear graph, abstract mathematical structure defined in two sets. Nodes, edges. I have a bunch of nodes and they are connected via edges. This is another representation. What this helps us is in a lot of code-based testing, integration testing, where we know that we can relate one entity or multiple entities by edges, and edges could become that relationship. Like flow of control from one statement to the other. Define a use relationship. I define something somewhere and then I use it in another particular statement. So I can define in one node and use in another. Things like degree of node become the popularity index, my connectedness. Or incidence matrix tells me if certain node is unreachable because it's not connected at all. Or adjacency matrix, which helps us in paths, concept of a path. Which then brings us to a level where we could actually use a graph to represent a program. And it's the same graph that we actually learned in our data structures. Graph is a data structure. We can represent airline networks. And when we look at such a graph from N1 through N7, it could be a series of statements. There could be a predicate. There could be a choice made. It could be a directed graph. Then I know that it can only go in the direction of the arrow. And it can help us in testing. How does it help? Well, in case of path testing, you will be able to make a choice from N1 to N7 by picking up unique paths. And we'll be sure through a graph theory that we have indeed covered all the paths, all the possible paths, all the basis path. That is what graph theory can help us. Thus, I think in this quick review, we have looked at some of the math concepts. You look for more during your classes, and then that is where it would be a complete piece how it could help you in your software testing. Thank you.